Welcome to the deep dive. Today we're tackling something pretty fundamental, the origin of the universe itself.
Yeah, it's a big one.
We got a request to really dig into the Big Bang Theory, and, well, we've pulled together some interesting stuff. First off, that name, Big Bang. It's a bit misleading, isn't it?
Absolutely. It really is. You hear Big Bang and instantly you picture some kind of massive explosion happening somewhere in space.
All right, fireworks.
Exactly. But the sources we looked at really hammer this home. It wasn't an explosion in space. It was more like the beginning of space and time, actually.
The beginning of space and time. That's hard to wrap your head around.
It is, because there wasn't a before in the way we normally think about it. No location for it to happen in.
Okay. So the core idea then is this expansion, starting from this unbelievably hot, incredibly dense point.
Right.
So forget the shrapnel image. Think more like, well, one source used the analogy of a balloon inflating.
Yeah, that's a good one. Imagine drawing dots on the surface of that balloon. As you blow it up, the dots all move away from each other, not because they're sliding on the rubber, but because the rubber itself, the space, is stretching.
Ah, okay. So that's like the galaxies moving apart. It's the space between them expanding.
Precisely. It's an expansion of space, not just through space.
Got it. And it wasn't like stuff crashing together that was already there.
No, not at all. The Big Bang was really the emergence of, well, everything. Matter, energy, space, time, all coming from this initial state called a singularity.
The singularity? Okay. What is that exactly?
Yeah.
In simple terms, if possible.
Well, simple is tricky here. It's basically the point where our current physics just gives up.
Writes down.
Completely. Imagine infinite density, infinite temperature, the laws of nature as we know them, general relativity, quantum mechanics.
Yeah.
They don't compute there. Gravity goes off the charts.
So it's less a thing and more a condition where our rules don't apply.
That's a good way to put it. So again, not an event in space, but the actual genesis of space and time.
Okay, so established. Not cosmic fireworks in an empty theater. It was the theater, the show, everything, starting right then. So what happened, immediately after this expansion started?
Right after, we're talking fractions of a second here, it was just unbelievably hot, insanely dense, basically pure energy.
Pure energy. Wow.
And as the universe expanded, incredibly fast, it started to cool down. And this is where it gets wild. In that first tiny, tiny sliver of a second, that energy began to condense. It formed the fundamental particles.
Basic building blocks.
Exactly. Things like quarks, electrons, photons, this stuff everything is made of, just popping into existence from that energy.
So the ingredients for matter just appeared from this super hot soup.
Pretty much. And then, still really early on, within the first few minutes, our sources say these quarks started clumping together.
To make protons and neutrons.
That's right. Protons and neutrons formed very quickly, and then they started fusing.
Fusing, like in the sun.
Similar process, yeah, but happening everywhere. This was Big Bang nucleosynthesis. Basically, creating the nuclei of the very first, simplest elements, mostly hydrogen and helium.
In the first few minutes.
In the first few minutes. And what's really cool is that the amounts of hydrogen and helium predicted by the theory, based on this process, they match almost perfectly what we actually observe in the universe today.
Ah, so that's strong evidence for the whole picture.
It's considered one of the key pieces of evidence.
Okay, so first few minutes.
Yeah.
Energy to particles, particles to nuclei, hydrogen and helium cores, basically. But still way too hot for actual atoms, right? The electrons couldn't settle down yet.
Exactly. The universe was still this incredibly hot, dense plasma, like a fog of charged particles, protons, nuclei, electrons, all whizzing around. And crucially, this fog was opaque. Light couldn't travel freely through it.
Just scattered immediately.
Right. It stayed like that for quite a while, relatively speaking, until about 380,000 years after the Big Bang.
380,000 years. Okay, what happened then?
The universe had finally expanded and cooled enough, still hot by our standards, but cool enough for the electrons to slow down and get captured by the atomic nuclei.
Forming neutral atoms.
Yes. Suddenly, you have complete neutral atoms of hydrogen and helium. And this was a massive turning point because, without all those free electrons scattering light, the universe became transparent.
So light could finally travel without bumping into things.
Exactly. Light was set free, you could say.
And that light, that ancient light from when the universe first cleared up, that's the cosmic microwave background, the CMB.
That's precisely it. The CMB is essentially the afterglow of the Big Bang. It's the oldest light in the universe, released about 380,000 years after the start, and it fills all of space.
And our sources describe it like a snapshot, right? A picture of the baby universe.
A very accurate description. And it's not just a uniform glow. There are these tiny, tiny temperature variations in the CMB, almost imperceptible. Those tiny fluctuations correspond to slight differences in density in the early universe. And those slight differences were the seeds. Seeds.
The seeds that gravity could then work on over billions of years, pulling matter together to eventually form stars, galaxies, and all the large-scale structures we see today.
Wow. So the CMB isn't just leftover light. It's like the blueprint.
It really is an incredible source of information about the early universe.
Okay, so we've traced it from the singularity, well, the start of expansion, through particle formation, the first elements, and then this first light, the CMB. That's an amazing journey.
It is.
The elephant in the room, right?
The question everyone asks, what started it? What caused the Big Bang? Our sources get into some theories here, and it sounds like things get pretty weird.
They absolutely do. Because honestly, that's one of the biggest unanswered questions in all of science. What caused the Big Bang? We don't have a definitive answer, but we do have some fascinating hypotheses.
Okay, like what I saw mentions of quantum fluctuations. Sounds floaty.
It kind of is. So in quantum mechanics, empty space isn't really empty. It's like fizzing with activity on a tiny scale. Virtual particles pop into and out of existence all the time.
Right, the quantum foam idea.
Sort of, yeah. So one idea is that the entire universe might have begun as a quantum fluctuation, but like a really, really big one, a fluctuation in some sort of pre-existing quantum field or vacuum state.
So the universe just popped into existence randomly due to quantum weirdness.
In a nutshell, that's the idea. Maybe like quantum tunneling, where a particle can overcome an energy barrier it shouldn't be able to.
Yeah.
Perhaps the universe tunneled into existence from, well, maybe not nothing, but from a quantum potential state. It's mind-bending stuff.
Yeah, no kidding.
Yeah.
Okay, what else? Inflation theory came up a lot.
Right, inflation. Now, inflation isn't strictly about the absolute origin, the T0 moment. It's more about what happened an infinitesimal fraction of a second after the Big Bang started.
Okay.
The theory proposes that the universe underwent this period of incredibly rapid exponential expansion. Like, it ballooned in size almost instantaneously, much, much faster than the expansion rate we see today.
And why propose that? What does it explain?
It helps explain some key observations about our universe, like why it looks so incredibly uniform and flat on large scales. Inflation would have stretched out any initial wrinkles or irregularities, smoothing everything out.
So it sets the stage for the universe we see, even if it doesn't explain the absolute start.
Exactly. It's a crucial part of the modern Big Bang model for many cosmologists.
All right. Then there's the multiverse. Always a popular one.
The multiverse. Yeah, this idea suggests our universe might just be one bubble among potentially infinitely many others.
Bubbles in what?
In some larger cosmic landscape, maybe? Some versions, tied to ideas like eternal inflation, suggest that new bubble universes are constantly being created. Our Big Bang might just have been the birth event of our particular bubble.
So our entire universe, everything we can see and comprehend, just one small part of a potentially infinite cosmic sea.
It's a staggering thought, isn't it? But it arises somewhat naturally from some interpretations of inflation and string theory.
Okay. And cyclic models, like the Big Bounce.
Yes, that's another angle. Instead of a single beginning from a singularity, maybe the universe goes through cycles.
Expand, contract, repeat.
Something like that. The Big Bounce idea suggests maybe there was a previous universe that collapsed inwards, a big crunch reaching a super dense state, and then it, well, bounced. That bounce triggered the expansion we call our Big Bang.
So no absolute beginning, just endless cycles, a cosmic reset button?
Potentially. It avoids the singularity problem, in a way, by having something before the bounce.
Interesting. And lastly, string theory and brain collisions. This sounds very cutting edge.
It definitely is.
Yeah.
String theory views fundamental particles not as points, but as tiny vibrating strings. And a related idea, M theory, involves higher dimensions and these things called brains, short for membranes.
Okay.
Imagine our entire three-dimensional universe as one of these brains floating in a higher dimensional space, sometimes called the bulk.
Right.
The theory goes that maybe our Big Bang was triggered by the collision of our brain with another brain in this higher dimensional space.
A cosmic fender bender in higher dimensions?
Kind of. The energy released in that collision could have heated up our brain incredibly, providing the energy and conditions for the Big Bang expansion to start within our dimensions.
Wow. Okay, so quantum jitters, super fast stretching, bubble universes, cosmic bounces, or interdimensional collisions.
Those are some of the main contenders, yeah. And it's really important to stress, like our sources do, none of these are proven. They are theoretical frameworks, hypotheses scientists are exploring.
Right. Still very much open questions. It really shows how much we're still figuring out.
Absolutely. Each idea pushes the boundaries of physics and cosmology. They're driving research, but that ultimate cause, still a deep, deep mystery.
Okay, so let's try and pull this together. The Big Bang. Not an explosion in space, but the start of space and time.
Check.
Started incredibly hot and dense, pure energy, which cooled and condensed into the first particles.
Quarks, electrons, photons, yep.
Then very quickly, quarks formed protons and neutrons, which fused into the first light elements, mostly hydrogen and helium. Big Bang nucleosynthesis.
Within minutes, yeah.
Then, about 380,000 years later, it cooled enough for neutral atoms to form, making the universe transparent.
Letting the light loose.
And that first free light is the cosmic microwave background, the CMB, which acts like a baby picture of the universe, showing the seeds of future galaxies.
Couldn't have said it better. It's the oldest light we can see.
And the cause of it all. Still unknown, but we have fascinating ideas. Quantum fluctuations, inflation smoothing things out. Maybe we're one bubble in a multiverse, or perhaps part of a cosmic cycle, or even the result of a brain collision.
A whole range of really mind-stretching possibilities, none confirmed.
Exactly. And as the material we looked at really highlights, this theory, the Big Bang Theory, it's not just science, it's kind of the story of everything, isn't it?
It really is. The origin of time, space, matter, energy. It underpins everything else in cosmology and astronomy. It's the foundation.
It's pretty awe-inspiring when you think about it that way. But it leaves us hanging with those huge questions still.
Oh, absolutely.
Like, was there anything before? If space and time began then, what does before even mean?
The ultimate question, perhaps.
And why? Why is there something?
Yeah.
Why not just nothing?
The why something rather than nothing problem. Philosophers and physicists both grapple with that one.
And are we it? Is this universe the only one? Or are we just a tiny speck in a vast multiverse?
These are exactly the questions driving the next generation of cosmological research and experiments, pushing the boundaries.
Yeah. It's incredibly humbling, actually. Thinking about this quest, trying to trace everything back to that single point or whatever it was, it doesn't make it less wondrous. It kind of makes it more so.
I agree completely. The more we learn, the more profound the mystery seems in some ways.
It definitely invites all of us to just keep looking up, keep asking questions, and appreciate the sheer scale and mystery of it all. Thanks for taking this deep dive with us today.